I'm delighted to welcome Tony Stelliga as our speaker in the View from the Top series. So for those of you that haven't come to these View from the Top series, you know this is not your weekly, bi-weekly, bi-monthly, bi-quarterly, whatever seminar series. It's a pretty exclusive seminar series designed to bring leaders in technology and business to come and tell us about really the view from the top and a little bit about how they got to the top, we hope, as well. And so it's a real great pleasure to hear from Tony Stelliga. I want to tell you a little bit about Tony before really pushing the floor to him, and I'll keep my remarks brief since I'm sure you're all here to hear Tony and not me. So Tony is Canadian and has been the CEO of Quellan since 2003. The company Quellan makes chips, integrated circuits that boost signal strength for mobile communications and other uses, and I'm not going to tell you any more. Though I will say that you'll find Quellan chips in connectors, receiver modules, and handheld mobile devices, and I'll leave you with that because I think you'll get more during the talk. Before he joined Quellan, Tony held several strategic positions at Intel, including as general manager of the optical processing division. He really led Intel's entry into broadband networking, and for this he earned the President's Intel Achievement Award in 2002. He also has experience, in addition to Quellan, of course, of startups. He founded and led Softcom Microsystems, which create leading-edge network processors for backbone routers and enterprise switches, serving firms such as Cisco and Nortel. And Tony sold Softcom to Intel in 1999. He earned a BS in computer science and an MBA from the University of Harvard. He holds 20 patents in broadband networking and processing architectures. Of course, none of this was reflected in the poster that you saw advertising his talk. I don't know how many of you remember. The poster actually is a tribute to his other interest. It is British sports cars. He's helping to revive Marcos Engineering, which is a 50-year-old British firm known for its classic high-performance cars. So, with that, let's give a warm welcome to our speaker, Tony Stelliga, who will tell us about engineering your roadmap to success, trends, thoughts, and lessons learned in the engineering world. Welcome. Those of you that are coming late, don't forget to pick up your box lunches in the back. Okay, I think you're all right.
Thanks. Thank you very much. And thank you for having me. Please come on in. There's a few more seats. Those that come in late have to sit at the front, of course. So there you go. Let's get started. As I said, it's a pleasure to be here. I'm a big fan of Berkeley and what you guys are all about and what you're doing. I had to do what you're doing in Ottawa, Canada, beside the world's longest skating rink in the winter. I went to the University of Ottawa, which was a much colder experience. You guys are right here on the doorstep of Silicon Valley. And I think you've got a great program, a great faculty, and I'm a big admirer of what you're doing. What I want to talk about today is give you a little bit of my background, just so you've got some reference, and then I'm going to talk a little bit about some of the lessons I've learned and some of the things that I look for now in hiring, recruiting engineers right out of school or with experience. I'm going to talk a little bit about the personalities of different companies or the DNA of different companies that you will experience undoubtedly, especially when you go out into the workforce for your first, second, or third job or the beginning of your career. These companies have different personalities. There's some things to look for that I've learned, and I think it's a good perspective on the type of companies to look for in terms of where you might want to be spending your hard-earned time after you get out. And then some trends to watch at the end that are relative to the experiences that I've had. So a little bit of background, and Dean Sastry talked about a fair amount of this. I went to the University of Ottawa, EECS degree. I was originally a modem switch IC designer, so I have a systems design expertise or experience set. I was the VP of engineering at LSI Logic, which developed the industry's first system on a chip, ASICs, and we took that company public. And then I was at Newbridge Networks in Canada, where we spun out what is now Tundra Systems, which is a public company, and then Softcom Micro, which we'll talk about as founder, which was acquired by Intel. And then as a hobby and to do a little bit of a taste of retirement there, I revived a famous British sports car company, which we'll talk a little bit about. And I'm also the director of Q-Sound Labs, which are the pioneers of 3D audio, and pioneered and developed all those algorithms over a decade ago, and now are a leader in that space. And I'm currently the CEO of Quellan, which is a wireless and wired noise cancellation company. How many of you are in electrical engineering? Just real quick. All right. And mechanical? So they kind of bunch into the front corner here. And I know we've got some materials guys as well, right? Okay, great. All right, so here we go. I think probably the overall overarching sort of message here is that you're in the midst of creating your runway or paving your runway for the future. And that involves really influential people that you'll meet, and many of them will be your peers, people you're working with right now. I was in a startup that was founded by the original founder of MIPS, which is I think a good term to use around here. And he was raising money for a new startup that was quite successful, and he was trying to figure out where to raise money, and I was in there and I was helping him out, and he said, no, I think I know where I can raise some money. I'll just go to Will. And I said, Will who? And he said, Will Hurst. And here we sit in the building, and it's Will Hurst III, the grandson, but Will Hurst became a venture capitalist at Kleiner, but before he was that, he was a roommate of the CEO of this company. So the people you're working with now, treat them nicely, work closely together. You guys are forming a bond that will go on for many, many years, and you'd be surprised where people end up. Many of my old classmates are customers, they're influential decision makers, they're investors. It is a very, very small world, and you're paving that part of the runway with the people that you're working with right now and you're meeting. I'm going to talk a little bit about experience that you will acquire. Are you guys doing work term placement stuff? Right? Are you doing work terms and placement? That experience is very vital, so we'll talk about that. And of course, ideas that you will design and implement. And what I want to talk about there is what differentiates a design from an actual product, right? What separates a good engineer from an excellent engineer in terms of some thoughts and some themes on that. And then, of course, patents that you will file based on your inventions. Ultimately, you'll generate corporate revenue for somebody else, for the company that you work for, which will turn into profit. But the ultimate goal here is to get a return on your hard-spent time here in the future, right? And so I'll give you some guidelines on that. So first of all, I think the underlying sort of issue that I see in what separates the good from the excellent, and I'm kind of opening myself up here in terms of even suggesting this, but because there's a question period at the end, but you really got to ask tough questions. And if you're not up to sort of walking up to somebody and asking those tough questions, be it a prof, somebody on the faculty, or when you get into the workplace, ask them of yourself, right? If you ask them of yourself, you will at least be in a position to sort of articulate that as you go through your day-to-day operation, your design reviews, what have you. And think of asking those questions to pundits, experts, faculty, your associates, customers, and as I said, even of yourself. In my first job, which really set the stage for me to be a strong system designer, my boss said, look, you can ask any question you want for the first 30 days because you're new here, right? Any question you want. After that, you're supposed to know the answers. All right. So think about that in terms of when you get out into the workplace or you get into the interviewing space, you want to be asking those questions. And I was very involved in a modem company in the early 80s, and they actually I secured my first job there. And I can remember going through the interview, and everybody was lined up. They came on campus to interview, and everybody was lined up. They all wanted this job. They were only going to take one guy, and it was probably the best job on the bill. And I went in there, and the rule was that they would give you a test. There was a test you had to write, and then they would proceed through the questions, and they would interview you. And I don't know how this happened, but I just kind of the way it worked for me. I went in there and sat down with the guy, and I started asking him sort of relentless questions about the company and where they were going and what I would be doing. And he passed me the test, and I wrote the test. And I got the job. And several years later, I was hiring some students, and I went through the file. And there in the file was my original test and my review information, and it said, can do two things at once, ask tough questions, hire. And the mark was irrelevant, right? It was that I was able to do a couple things at once and ask tough questions. So I encourage you to think about that in terms of how you look at everything from the designs you're doing to the experiments that you're running to the people that you meet, because this is a time in your career or in your life where you can ask a lot of questions and get away with it. So let's talk a little bit about Softcom. Softcom was a startup that I founded after I left Newbridge Networks. I came to Silicon Valley and started the telecom group at LSI Logic. We grew that to about $150 million in revenue. And then I left to start my own company, constantly asking those questions about why can't I start my own company, what would it take? And the idea was, from an engineering point of view, and it's sort of a good lesson, is to sort of look at how people are doing something now and sort of turn that around, turn it upside down, and look at different ways of approaching the problem. And what we did at Softcom was very interesting. We took basically the concept that was in fashion then, this was in the mid-'90s, which was to capture all the interfaces on some kind of a network router and dump all of the packets into memory and have the software do all the routing, do all the lookups, do all the TCP/IP forwarding. It was all done in software. And as a result, the routers were very, very slow, right? And they couldn't really scale because you could increase the clock rate by 10 or 20%, but it just didn't have any effect, right? So we looked at it very hard, and we asked a lot of tough questions of our friends at the big router company that was doing very well at the time. And we concluded that you could actually do a lot of the processing in the router in direct hardware. You could collapse. What is shown here is really a lot of the layer 2 and layer 3, and even do some lookups above layer 3, and capture the right mix of information and map those packets or those flows into dedicated pipes inside the fiber optic trunk. It's sort of like mapping passengers into an airplane, right? You want to make sure every seat's full, right, when that plane leaves, and the guy beside you might have paid 10 times what you paid. You might be traveling on travel points, but those seats all got to be full. So what we did is we made sure the fiber optic trunk was full with all kinds of different traffic by doing those lookups at wire speed in hardware. And this was very, very disruptive. The router guys were quite threatened by it. In fact, they threw me out of the first meeting. They said, this is crazy, you're threatening our franchise. We have all this software investment, and there's no way we're going to support you doing it in hardware. So we went to the underdog. We went to the number 2, number 3, number 4 players, and of course they were all very excited about this. And we got them to sign up, and they paid for the development of this because none of the venture capital guys would fund it because it was way too risky. If you get one transistor wrong in what was then a 5 or 6 million transistor design, it doesn't work, and you're dead, right? So we sold manufacturing licenses. We got companies to pay us advanced fees to get early access to it. And this became the industry's first network processor. And it really wasn't a processor at all. It did everything in hardware. But it accelerated the speed of the router by a factor of almost 10. Right? And I think that's the real sort of metric in what you want to be thinking about in the business or in the industry or in Silicon Valley. Is if you can have an impact of 10x, price performance, 10 times cheaper, 10 times faster, any combination of that, 10x is the number you got to hit to get anybody's interest, right? If it's twice as fast, it's going to happen in time, right? It's got to be about 10x. So this is what we were able to do about 30 months after formation of the company. The company was acquired by Intel, who were obviously and continued to be the leaders in microprocessors, but they didn't have any network processors. And there was a growing concern about that phenomenon becoming very, very important. They needed to have a product in that area, and we had all the customers because we co-developed this with those customers. All right, so I think the other point I want to make is don't view the relationship with a customer or with somebody that you sort of report to, as a firewall. It's really a mutual thing, especially if you can get their skin in the game. They needed this product. We asked them to pay for some of the development. They did. We needed them for credibility and for knowledge and expertise, and it was a win-win, right? So really work closely with whoever you perceive your customer to be. We went on from there to do another company, which I'll talk about. But before I do that, I want to sort of talk about communicating your ideas. We were able to very succinctly communicate to the router companies the speed performance they would get. We were able to package it in a PCI card that was about that big versus the big line cards that they had. And we used a very succinct set of demos and performance evaluations to communicate effectively our idea. And that really captured the idea. It wasn't just that it was faster, it was that it was already embodied in a form factor that they could get their hands on and they could use. There's a story that when the iPod was developed, they were running around trying to figure out how to get the message across to management about what it was and what it was going to look like. And they actually mocked one up. And to give it the right sort of look and feel, they actually put fishing weights in it so that it felt, it was just a box, right? It was a piece of cardboard. But to give it the feel so that when the big guy came along and grabbed it, it had that weight to it, right? Those are the kind of things that you want to be thinking about doing to make the product as close to the end mindset or expectation that your customer has so that they really feel like it can be done. All right? So some thoughts there in terms of communicating your idea passionately. Vividly is probably the word that I would use there. All right, so on to the wireless world. A couple lessons learned here. I hear a lot of phones going off here and there, which is understandable. It happens all the time. But in a lot of cases, you could be in a room or in a meeting, and you walk out and you got 3 voicemails, and your phone never rang at all. And you wonder, how did that, I missed that call. I wanted to get that call. Right? That was a call from my friend. We're supposed to meet up somewhere. What happened? Well, what actually happens is that when you get into a weak coverage area, right, the signal strength gets weaker and weaker as you get further and further away from the base station, as you get closer and closer to an indoor scenario. And the noise of the phone actually becomes the predominant aggressor or the predominant signal that the antenna sees, right? It's the noise from the display, it's the noise from the camera, it's the noise from the actual memory system, right? So your signal-to-noise ratio degrades because the signal's getting weaker and weaker and weaker, and it's approaching a noise floor. And that's really what this diagram is showing here, right? The signal is actually buried underneath this noise floor. Normally it would be way up here. But as you move away from the base station, it gets weaker and weaker and weaker, and ultimately it gets drowned, right? It gets submerged, right, by the noise. But this noise floor is actually artificial, right? It's deterministic. It's generated by the DRAM system, the power amplifier, the camera, the display itself. And you can actually tap into that or those noise sources and turn this no signal scenario here into a signal where you really have inserted what looks like an active notch into the passband of the antenna, exposing the signal from the noise. It's almost like drawing the water out from around the iceberg, right, or pulling the gold out from the ore. And if you do that, you can get 4 or 5 bars of signal strength back on your cell phone. And we call this in-band adaptive noise cancellation, right, at radio frequencies. It's Dolby for cell phones. It's Dolby for antennas. And it's very revolutionary. It's very disruptive. It's got a series of patents and development that we've done over the last 3.5 years. The patents issued in late 2006. We made 40 claims. All 40 claims were accepted. Brand new territory. This is electromagnetic modeling and subtraction, or modeling and cancellation. And the results are very profound. In fact, what we're doing here is really, in simplistic terms, listening to the actual noise through a tapping technique that is actually mechanical. Right? We do a near-field detection of the noise. We then model the noise in amplitude, phase, and frequency. And we insert a correction signal into the passband or into the antenna that's 180 degrees out of phase from the noise. And if you do that, you can get 4 or 5 bars of signal strength back on your cell phone. Right? No more, I didn't get your call. All right? Now, the other thing that's interesting here is that, it's sort of, to draw an analogy here, this is the sort of same thing that you do in the graphics world, right? What they do at NVIDIA is they model colors in RGB, and they pick one of 24 million values for each, and that gives them the exact resolution, right? The exact color that they want. So we're doing the same thing here, but we're selecting the algorithms, or using algorithms here to select the values that run on the chip. So it's really an embedded system. It's like a tuner that's tuning out the noise from the handset. Algorithms, circuit design, and mechanical insertion techniques give it 3 corners of intellectual property protection. Right? You've got software algorithms that are patented, you've got circuit design that's patented, and you've got a technique or a methodology for tapping the noise. So the message I want to give you is think about everything, right? When you get a project, or you get your first assignment, or you get your first, be the first lead on your first project, you don't want to spend too much time on this. But you want to think about the entire system as much as you can, because there's a lot of value in the fringes that you want to capture in the embodiment of the product. And by doing this, we were able to have a complete product, a complete solution that solves the problem without having fragments or pieces of it and leaving room for others to come in as competitors, right? Problems getting worse, as you guys know. Displays are getting bigger. Cameras are getting higher resolution. We're seeing a huge uptake in platforms that have noise, satellite radio receivers. We're even involved in the data center where we've got activities in removing the noise from cables that are used in big data centers so they can reach much further and run much faster. Right? So noise is a profound problem. It exists across the enterprise, in broadcast and entertainment, wireless handsets. Even in the automotive segment, we were brought in to solve a problem in Asia. It was in Japan. We were brought in and they said, look, we've got a real problem here. There's a brand of car that can get through any electronic toll reader, any bridge toll reader for free because the noise from the ignition system floods the receiver for the toll reader. And you need to help us right away. So it was very exciting. Can't tell you what the car was. But it would be a great fleet car for somebody that was a sales guy, right? But you can tap the noise from the ignition system. It's very tappable. And you can emulate it or model it, and you can subtract it from the toll reader receiver. So noise is a very, very broad problem, right? It exists everywhere. In fact, the industry has spent decades protecting the signal, but never really worried about the noise. You could view this as it's a very small embeddable device. It's so small that it can actually go into, let me grab that picture there. There it is shown on the Liberty coin there. It can actually go into another IC. It can go into a connector. It turns out that when I was at Intel, we measured our die size in centimeters. That was cool. 2 centimeters on the side was a pretty impressive device. In the analog world, at Linear or Maxim or whatever, they measure the die size in millimeters. Pretty small millimeter kind of die size, right? Very inexpensive. We measure our die size in microns. Right? These devices are so small that they can be embedded into other people's ICs, GPS modules, TV tuner modules, so on and so forth. So just for the fun of it, I'll pass these around. I got a couple of them. We'll send them each way. And in the center of the logo, you can see how small the chip is. And for those of you that are working in the fab or the nano fab, the biggest yield loss we have is in the scribe line, where we lose 30% of the die because of the scribe line. Right? So it's a very, very small die. Have a look at it. I hope to get it back, and I'm keeping a close eye on those materials guys back there that were asking questions earlier. But that's a very disruptive technology. It's small, so it's very economical. It's pervasive, and it effectively improves the receiver by about 20 dB for 50 or 60 cents. Right? Very unheard of. So, sorry, picture missing here, but this is an example of what we can do. We can take a GPS receiver in a handset, and we can reduce the lock time from about 3 or 4 minutes to just 20 seconds, right? Because there's no noise around the receiver to affect its ability to correlate to the satellites. And we can improve the accuracy from about 1/4 of a kilometer to less than 40 meters. And as you know, Starbucks are now within 40 meters of each other, so you got to have that resolution, right? But for location-based services, you got to have instant lock, and you got to have accuracy. And you can't get that right now because there's too much noise in the cell phone that floods the receiver. So you cancel the noise, and off you go. All right? So what have we done a little bit differently here? Something to think about again. Customers, asking tough questions. We've assembled a list of investors that are venture guys, but also our customers. Right? And believe it or not, Samsung is an investor. TSMC helps us with the scribe line problem. They're an investor. Recently, W. L. Gore and Associates, that are featured in the Crossing the Chasm, one of Malcolm's books, invested in us. These are the guys that invented Gore-Tex. They make advanced cabling. It has a lot of noise in it. They want to get the noise out. And so they use silicon to do that from Quellan. All right. So present your case, right? Relentlessly, right? Don't give up. A lot of people believe that the 3 cornerstones of this, again, were too difficult, like the network processor. You've got mechanical issues, you've got software issues, right? If there's a problem to be solved, stick with it, right? And don't spend too much time thinking about how difficult it is. It's easy to give up, right? Just keep looking forward and present your case as relentlessly as you can. Because if it was easy, everybody else would be doing it. It took us 4 hard years to get this done. When the patent's issued, it was really only the beginning. But now we're in a stage where we have a very, very unique product. All right, so what we talked about were 2 companies that have sort of a similar theme. They're both very disruptive. We disrupted the router franchise by doing it in hardware, and we and we disrupted the signal-to-noise or signal integrity of various receivers in the marketplace with a very, very low-cost device. So we consider that disruptive because nobody else has it, right? It resets the price-performance metric in the marketplace. And it's something to look at or something to think about as you go forward here. And you can think of various disruptive companies that have this kind of position, right? Tesla is a good example, right? Electric car. Usually when you have a disruptive companies, the big guys don't like you. They hope you go away, right? And this is the kind of dynamic that you require to really technologically be disruptive in the marketplace. Cadence was a disruptive company, probably 20 years ago when they allowed, or Synopsys, where they allowed people to start to synthesize their own designs instead of capturing schematics, right? You can think of many examples of companies that were technologically disruptive and had a huge impact in the marketplace. I think it's the easiest way to get in, but it takes the longest because you've got to have software, you've got to have an ecosystem, you've got to have a lot of evangelism if you're going to survive as a disruptive company. So when you're out there looking for and talking to people that are interested in hiring you, the characteristics of these companies are they have revolutionary technology, there's no one else in the marketplace that's done it, and they have no competition for a while, right? They have no competition. Very fun place to work at, very, very focused. What you're looking for is an evangelist, management team, a driven CEO, superb engineering, great marketing, and as I said, you've got to have a complete ecosystem, right? Tesla's got to figure out where you're going to charge your car up. They got to figure out where to get the batteries. They got to figure out the dealer network, right? But if you can get it done, the dividends are huge, right? It pays huge dividends, and it's very, very rewarding. So something to think about. The other type of company that we see out there, and these are all equally important, it's just sort of a perspective for you, are what we call time-to-market companies. And this would be some of the wireless LAN guys, Atheros, for example, that was first with the product. You just happen to be there first. You focus on one product, you focus on a time window, you get it done, and you're first to market. Lots of people have wireless LAN chips now, right? But the guy that was first really reaped the benefits, and I'd say that's a company like Atheros. Execution and economics, right? Execution is about being tough, being focused, and just having more product, faster, cheaper, less expensive than the other guy, right? And it's about executing on delivering a product that has competition, but at a lower price and at a greater value proposition. NVIDIA is a good example. Graphics chips have been around forever. They out-executed everybody, right? So execution plays tend to be, MediaTek is another example, right? MediaTek is out of Taiwan. They are now the largest cell phone chip provider in China. They surpassed TI last year. Lots of people have PAs, power amps, LNAs, but they are the guys that have the largest market share in just about 7 years, right? Now, what you see when you're raising money is that a lot of the companies that are execution-focused come out of Taiwan, out of China, because they are just relentlessly focused on getting every cent out of the product. They're very, very good at it. And we're seeing a lot of activity in that space where your engineering acumen there is smallest die size, fastest design time, and broadest product breadth. Okay. Branded companies. Sorry, some of these logos aren't coming through on the.
Are those movies?
No, they were generated on a. This is actually an Apple logo right here. They were generated on a Mac, and something got lost in the conversion, but no worries. So Apple's a good example. Dell's a good example. I like the Burton example. There's a brand. It's not technologically advanced, but there's a brand that's done very, very well with a very broad horizontal product line, tremendous scale. They've gone from doing, snowboards in a garage to clothing to merchandising. And branded companies you may end up working for, right? They're great companies. They have a lot of different groups. They have a lot of different sort of dimensions inside the company. But consumer-branded companies are becoming very, very popular in terms of their adoption and their migration towards technology. So some different perspectives. Disruptive is where I like to play. I think it's got, from an engineering point of view, the most excitement. And it's something to think about in terms of the different kinds of companies. Now, there's one more that's kind of interesting. It's kind of sit back and relax and think about it for a second, but it's retro, right? A retro company that harkens back to the emotional character that we all sort of remember or want to resonate with. This is a tube amplifier from Tri Corporation in Japan. I don't know how many of you are audiophiles or if any of you are musicians, but Hammond or Moog, who make the synthesizers, you buy one today, it's still the wood grain thing. You pay $10,000 or $12,000 for it. There's a huge resurgence in tube amplifiers because they have a warmer tonal quality than transistors. And these guys have had to retool to get the tooling for the old tubes. They're doing really well, and it harkens back to the sound quality that people want from the past. Right? These are fun companies. I call them retro tech. The characteristics are they stir emotion. They harken back to an era with advanced technology nonetheless. And they have a subjective value. People will pay a ton of money for these. Not based on the cost, but based on the way that it is perceived to or actually sounds. So you want to have great marketing and a very solid team dynamic in this kind of company. But we're seeing more and more of them as emerge. And of course, your PR people picked up this picture of me on the internet that's used in the poster. And it was a shot that was done by the New York Times with another sort of retro play. And that is the Marcos engineering revival that we did. The mechanical guys are over here, so I'll kind of look at you when we go through this. But it was a retro play, right? It's a famous brand that was around in the 60s, very celebrated. A lot of victories, raced at Le Mans, British GT champion several times. This is a car that was used in The Saint, various movies, and Jackie Stewart won his first race actually in 1962 in a Marcos. Company went bust. Loved the sort of essence of these cars, and came in, bought the tooling. My son and I bought the tooling, and we decided to bring back this celebrated British brand. And it's a retro play, right? It's a brand new car. It's totally retooled. It's totally redesigned. You can see some of the specs here: 500 horsepower, very lightweight composites, very fast, and it's hand built. All right. Many of the watch companies are kind of retro too, right? These are retro plays, and I got to tell you, it's a lot of fun. I should probably add to this that we did our own electronics to sort of tie it into the presentation. We were able to do work on the power curve, and the car is so light with a Corvette V8 engine in it that it will actually pull about 32 miles per gallon. Right? It weighs just over 1 metric ton. Right? That's how light it is. So you can lug around. When the reporter came from the New York Times to drive it, you get people over there and they're on the wrong side of the road, and they're all disoriented. So he went to pull out of the factory, and it's first, second, third, fourth. It's retro, so it has a stick, right? None of this paddle stuff. So he had it in third gear, pulled out, didn't even know he was in third gear, thought he was in first. It has so much low-end power that it will go from a standing start to 150 miles an hour in fourth gear. You never have to change gears. Right? We move the power all the way down to the low end, right? So it would pull like a tractor. And so we did all those kind of hand-built tweaks on this thing. And I want to say that there's a shot of it here from the front. As I said, it was a lot of fun. I think some of your faculty would look pretty good in this too. It's a British Corvette, right? It's 2/3 of the size, and it really harkened back to the spirit of what people wanted to see in a hand-built car. They were tired of the automated, mass-produced cars. This is really craft-produced, if you will, as opposed to mass-produced. And what we learned is that we could put a lot of students to work here. This is one of our students working in the factory. And I think the lesson here is that you've really got to get some experience as soon as possible, right? We spent about 6 years developing this before it went into production. It's insane, right? Not a lot of guys, right? But 6 years of getting this car right. Everything in the car is 100% bespoke. It's all custom. You won't see anything on it that represents something from another car. And we did a lot of work with students. In fact, Coventry University in the UK is the top automotive design school, I think, in the world. And we did a lot of work with the students there to give them some experience. And they all came in and they said, it's great because all of our buddies are over at Jaguar working in the library putting books away. And we get to come into Marcos and actually design stuff. We get to actually get in the car and do work. So for those of you that have the opportunity to do work placement, I've done it. I did it 3 times. I had an offer before I graduated from the company that I did my 3 work terms with. These guys all got placed. Those that we didn't get went on to Ferrari and bigger and better things from there. But it's really, really important to get that experience, even if it's not kind of directly related. We have had a student in from Berkeley at Quellan. He was there for work placement for about 8 or 10 weeks. Did a great job. We continue to do that. We've had students from other schools come in. I'm a very big believer in that. And it'll give you a chance, if we go back to the second or third slide, to meet people that will be influential in the future for you. So get that experience. And be happy to talk to you guys about that if you're interested. The other thing that we learned is, I'm just going to go ahead here, is it's great to be the underdog. When we had that company going, we had such a massive updraft and such a massive cheering section. There were thousands of people all over the world that wanted to see a small startup hand-build a car that was faster than any mass-produced supercar. And we had support from all over the world. So I think that the lesson here is that if you go into a startup and you have disruptive technology, you don't want to pound your chest about it. You want to go in, you want to be humble, you want to ask people for their inputs, you want to get people's skin in the game, you want to get them involved or have a stake in what you're doing. If it's your thesis, your experiment, your project at work, or anything you do, you want to get the people around you involved in the project. And as an underdog, it kind of positions you that you're in an underdog position where the expectations are reasonable, right? No one's looking for you to take a fall, right? The expectations are that they want to help you. And in the car company, that was really a strong lesson that we learned, was it's great to be the underdog because it really creates a strong alliance with those people that normally would be our enemies. We were getting parts built at the same factories that, Aston, all the top cars build their products, right? Bentley, same guys, same stuff. Because they felt that they had skin in the game in our project. They wanted to see us succeed. So you go into these factories where they were building components for our car, the totally outsourced model. And you'd see all these very, very expensive British cars going through. And on the wall, you'd see a poster of the Marcos. Because they felt that they had skin in that game, that they could really have a say and an input into how that car was put together. So think about that when you're on the providing side, right? Get people involved in your project. The final one that we learned, which is what took us a long time, was you don't want to design to be on the edge here. You want to design with margin. And I know when you guys are doing your experiments, some of your lab work here, you just kind of want to get it. You got to get it done. You got a deadline. But what you want to do is make sure you design with as much margin as you can for a couple reasons. One is it really sets apart a good designer from an excellent designer. The margin problem won't show up till later. Right? It'll show up in the factory. It'll show up a year later when the product's in production. They tweak something in the factory in the process. The margin's gone, the part doesn't work, and they know where to find you. Right? It's not a pleasant experience, and it's really something to think about in terms of designing for margin. We had so much margin in this car because it was so light that we could constantly unleash new performance packages for it. We could constantly unleash new specs for it and new variants of it because there was so much margin in the way that it was actually designed and put together. And I guess the other message is keep that margin to yourself. Any unused margin, if the marketing guys find out about it, they'll take it and put it in the product, right? So the time to get margin isn't necessarily when you do the design. It's when you negotiate the specification for what you're designing, right? Keep it in your back pocket then. Because by the time it's out there, you don't have much room, right? So negotiate win-win if you can, right? With your customer, with your boss or whatever, to have enough margin in your spec that you've got some freedom in the future if you have to make design compromises. And generally, I think what we're seeing here is there's not, that philosophy is kind of going away, right? There's so much pressure on time to market that there's less and less margin in the design. All right, so let's wrap up here. I want to go through just a quick final slide here. This is a slide that shows sort of a historical perspective from where I've been at, and I guess it goes back to when I started my engineering work in the Valley, and it goes from sort of 1980 all the way forward to 2010, and there's a sort of cycle here of increasing what I call change in innovation per unit time, right? Change in disruptive innovation, DDI, over a change in time. And way before your time, things were basically logic or electromechanical. But in the 80s, we went through a functionality phase where we started to build, ADI started to build converters, companies started to build microcontrollers, SRAMs, so on and so forth. In the 90s, where I started to get, this is sort of where I entered the workplace, was in this area here. We started to get to integrating that stuff. ASICs were born, CAD tools started to evolve, Cadence came on the scene, The synthesis tools came on the scene, and we went through a massive integration phase. Huge innovation there in terms of CAD tools, design margin, getting custom silicon out. But then in the sort of late 90s, and by the way, these tales last all the way. I'm not saying there's no more innovation going on in integration, but we went through a phase here which was digitization. Very important phase from an engineering point of view. We started to digitize everything. We digitized the internet. We digitized the cell phone. We digitized satellite radio, right? And what we did was we used that digitization to sort of move everything over IP, or over the internet protocol, right? Everything went digital. Audio went digital, so on and so forth. The challenge there was all we were doing was digitizing and dumping. We would digitize with a converter, throw it into a bunch of memory, and have the software guys figure out how to run algorithms on it, right? And those algorithms would be run on a DSP. It would run as fast as it could. You wanted more speed. But it was all being done in software. So the good news is we were digital. The bad news is that we really weren't able to add any value at the point of conversion. So what I want to talk about here is the next wave here. And I would call it a massive wave of specialization based on these three themes. But it is really the sensorization of the electronics industry, right? And what we're talking about by that is the shift of value from the bucket that does all the math and all the processing in memory and the converter to a point before that, which is the actual sensor, right? And that sensor started off as a manifold air pressure sensor or an oxygen sensor in the automotive world from a production point of view in the late 90s. But we went through inertia sensors with the whole, accelerometers, so on and so forth. Very interesting. But where we're headed now is, there'll be 1 billion MEMS microphones shipped in 2012. Right? The old microphones are gone. Right? Everything is going to a specialized sensor. This RF electromagnetic sensor here, RF-EM, is our noise canceller at Quellan. Right? It is a sensor of sorts. It senses noise. It processes it. Right? So huge innovation here in the sensor side. And you're going to see all this done on standard semiconductor processes. So the sensors won't be CMOS. They'll be what you guys are working on here in the upcoming lab and over at the Citrus Center and the projects that you're doing, right? They'll be built on a semiconductor framework. So they'll be very economical, but they'll be very, very specialized. And there'll be a huge shift in value from the diminishing returns on the processing side and the diminishing returns on the converters being faster to the sensors being much more intelligent and much more application specific. Right? I was just reading a report the other day that in 2010, which is 2 years from now, less than 2 years from now, the market for chassis sensors on a car, where you're sensing that body roll, will be $2.5 billion. Just for a chassis. Imagine what it will be like, for light sensors, camera sensors. Everything is going to a much more sophisticated front end or sophisticated sensor. So call it what you want. It really is sensors over semis. It is microelectromechanical. I think you guys are on the verge of it right now. And I'm not just saying it, but it is a major thesis in terms of where I think the semiconductor industry is going to go. And that's not to say there isn't any more innovation in these tails. It's just not disruptive innovation, right? It's ongoing innovation. But this is where the disruption will be in the shift to this sensorization. So having said that, I wanted to thank you for your time and open it up for questions. Thank you.
Okay, we have time for a few questions. Since we're recording this, I ask you to speak to the microphone. Oh, the mics. Okay, fantastic. Just
you're live.
I wanted to ask you about engineering economics and problem finding, because having the right nose for where to go. Engineering economics kind of determine kind of your kind of parameters, but knowing where to go, that's where a lot of the talent is. And I think in research, we often develop certain senses of interesting from a research perspective. But then there's the added factor of the industry about what you can do in business. So I wondered if you could talk about that balance.
Yeah, no, very good question. And we touched on it a little bit, but let me elaborate. So where to go, versus, or where to take your research and where to apply it sort of commercially to win is, I think, what's behind the question. A couple things come to mind. One is that you've got to look at engineering as not just an economics, making it cheaper or economics exercise. I said earlier, a price performance win of about 10x is something that will attract anybody's attention, in the industry. Now, you might say, okay, it's 10x cheaper, but I think what you want to do is start with sort of 10x on the performance side, right? If you can do work that yields a performance increase of 10x, there's always a capability coming up that can reduce that to practice, right, in terms of the economics, right? When we were at Softcom, the philosophy was go get the socket in the rotor. Get the socket, get the software out of there, get the hardware in there, and then we'll worry about how to tune the cost out of the product. And I think often there's a lot of work going in making the cost just right, spending all that time to get the cost right, and by the time you show up, the customer's not interested anymore. So number one, you got to get out there early with your concept. It should have enough disruption that it's technologically performance warranting their interest. And number two is you've got to get to know those people that I was talking about in the second slide. Those are the people that are marketing people. I don't mean traditional marketing people. I mean people that have a technical background or good marketing people that know people that have a problem. I've always asked the customer what the problem is, right? Not what I have, but what the problem is. And I think that's very, very important. They will tell you what the problem is that they're having if you sit down and listen. So engineer for the customer's problem, engineer for performance, and don't worry too much about all the cost breakthroughs because that's going to take a lot of time and it's not necessarily going to be the thing that you want to lead with. That's my advice. Yes, sir.
How cost-effective are patents versus staying one step ahead of the other guy or keeping company secrets?
Good question.
This is an ex-Bell Labs guy.
All right. The patent question. Yeah, I didn't have much time to talk about that.
Jeez, the camera has gone nuts here.
You want to hear the answer to this one, huh? I think patents are the last sort of resort to any kind of deterrent by a competitor. If you rely on your patents, it's not worth it. It's not worth it. You've got to have many layers of protection before you actually get to the patent, right? And those layers are, it's just hard to do. It's encrypted. It has software and hardware. It's secret. We waited to launch the company for 3 years until the patent's issued, right? So those are the things that you want to do. A patent is really something that says it's yours. You can use it as a bargaining chip if you need to in the future. And it does create value, but it's not necessarily immediate value in terms of a monetary issue. It's more of a protection card that you have if you need it in the future. So the biggest barrier is being first, no one knowing about it until you surface, and having a design technique or a design architecture that's just really hard to copy.
Hard questions. Jan.
Yeah, I saw your. I was very interested in the GPS work you did. Are there any devices on the market where people already use the technology you developed?
Yeah, good question. So we, in the GPS case, we have several modules, GPS modules, that will be coming out later this year that use the technology. We've got them up and running in our lab. They're being qualified. And our chip will be inside those modules. And those modules are typically about 5 by 7 or 5 by 8 millimeters on a side. And our device is in there. In terms of the cabling that I talked about, the noise and cabling, our products are in 2 of the top 5 supercomputer installations in the world to make them run on thinner gauge cable, make them run further so they don't have to use optics. And we save hundreds of kilowatts in the data center by going with these chips inside the copper cables. The other big market for us is mobile TV, where you can watch broadcast TV on your cell phone, but it's too noisy. So that's another type of module that will be in later this year. Yes?
Tony, so what's your thoughts about the convergence of the green industries and the sports car industries in the future? What's it look like here? 500 miles a gallon, or 500 horsepower?
I don't know. That's a good question. The 500 horsepower thing, I know what it feels like. Yeah, it feels good. It also feels good to drive by 5 or 6 gas stations in a row. So I think it's an important theme. I think the U.S. automakers, they're starting to get on with it pretty good now. They've got a lot of hybridization in the drivetrain, where you get assist in the gearbox. A lot of the commercial vehicles are getting there. But I think, the new CAFE rules, which say that every manufacturer has to basically increase their average miles per gallon by 1 mile per gallon every year through, 2020 or something? So they got to be at 35 miles per gallon in the next 12 years, is being taken pretty seriously. And I think it spells I wouldn't say the demise, but the entry of a smaller form factor kind of drivetrain. But I would say the most important thing from my point of view is actually the weight and the material in the car. There is so much baggage, so much excess weight in these cars. The chassis on that car is a space frame, so you can put your hand through it anywhere. It's like a ladder structure. It's air, apart from the actual composite frames. And the body shell is actually air, right? It's a fiberglass layer with a foam core that has air impregnated in it in the middle, right? So it's got a lot of air in it. It's very, very light. And the performance benefits are huge. We're getting 2.5 times the miles per gallon of any car that uses the same drivetrain. So I look for advances in composites, carbon fiber, a lot more aluminum, a lot more stressed parts as something that we're not really focusing on. And I think that's where the industry needs to spend a little bit more time. Everyone's worried about the engine, right? Replacing the engine or whatever. It's in the weight of the car and the materials that we're using.
In one of your slides, you had a partnership with the electric car guys, right? It was one of the missing icons.
Yeah, I was actually just referring to Tesla as a very disruptive company. A lot of their development's done in England, as you probably know, but it's a very disruptive company, and I'm watching it closely because it'll be interesting to see not only how they do, and they're having some tough times. They're a startup. They're using a lot of Silicon Valley techniques to do this, but also to see what the big guys do. Do they ignore them? Do they get them? Do they take them out? What are the dynamics of that in terms of where these disruptive companies end up? To have a disruptive company go from disruption to IPO is a rarer event, but it's a very, very substantial one. So watch that one closely.
Well, you did make the comment about the silicon industry being affected greatly in this next phase by the development of the MEMS and the necessity of those in so many products. If you look at from the MEMS side, there's a lot of disruption ahead for the silicon industry because many of the things that you want to do in MEMS demand new materials, new technology. I just wondered if you wanted to talk about that a little bit.
Yeah, I think it's interesting. I mean, if you look at the data reports, they break out advanced material sensors from sort of traditional sensors. In the IC world, there's always sort of a rule which is, don't bet against CMOS, right? It's got tremendous scale. I've seen a lot of work that's going on in CMOS that pertains to sensors, everything from light to inertia. So I think that market will do, that segment will do very well. I think the more advanced materials remains to be seen if they have enough performance to yield, the kind of pricing that they're going to have, and if they can really get to volume.
Just to comment on what you said, I remember very well when it was don't bet against T²L.
Yep. Yep. And don't bet against Ethernet was another one that was something to think about. But I continue to hold out a lot of hope for CMOS, and I think what I'm hearing is that from people I talk to is there's something in the middle here. There's an overlap in the middle where it's a standard CMOS template or foundation with a sensor overlay. So there's some hybrid work in the middle that's going on that I think is quite interesting. The problem is nobody wants to disrupt their fab, their CMOS fab that's running wafers that are generating $100,000 a wafer to do. So the concept of being able to apply that in a research environment and the work that you guys are doing, I think is very, very important. And working with industry to get that going will serve you very well. But the part in the middle, where you're borrowing as much as you can from CMOS, I think is where I'm spending most of my time studying.
That's certainly been the philosophy of the fab and now the nano. Questions?
I have a couple business cards going around, by the way. Okay? Anyway, I'm impressed. All right. Pass the test there.
We're not saying they're the ones you handed out. We're just saying there's
dies in this one, right? Yeah.
All right.
Yeah.
Well, before we sort of but first of all, we'd like to make Tony a honorary Cal alum. And this has a little bit of swag here. Small questions We're going to make sure that Troy gets a little chance to eat before he goes out and meets people.
You know where that's going, right? Yeah. That's great.
So if you have little things you didn't want to ask in public, this is your chance to come up and talk to him as well. So
Super.
thank you all very much.
Thank you very much. And good luck. Good luck. That's great. Yeah, no, thank you very much.